In this problem, we are going to consider an inelastic collision. We have a billiard ball of mass 0.37 kilograms, I'll call that M1, and it's moving at 3.98 meters per second, so it has some velocity in this direction here, when it strikes another ball of the same mass, which is initially at rest. So that's my first sentence. It's telling me that both of my billiard balls are actually the same mass. So M1 is equal to M2, that's 0.37 kilograms. It says that my first billiard ball is moving at 3.98 meters per second. So I'll call that V sub 1 initial equals 3.98 meters per second. And we said that this second mass was initially at rest. So V sub 2 initial equals 0 meters per second. It's initially at rest. This is what my system looks like before the collision. Then the collision happens. This is my initial system. Here, these dotted lines indicate that the collision happened. Those two balls smashed into each other. And then after that, they're going to move off. They're going to separate from each other, and then they're going to have different speeds. So after the collision, my first ball is now moving in the same direction with the velocity of 0.3 meters per second. With that information, we have to find the kinetic energy lost in this collision. So kinetic energy lost, KE lost, is what we're trying to solve for. Okay. Now, since this is an inelastic collision, we know that the energy is not conserved. That means the sum of the kinetic energy of my initial system is not going to equal the sum of the kinetic energy of my final system. We're going to lose some energy in the process, so actually the sum of the kinetic energy in my final system after the collision is going to be smaller than my initial kinetic energy. So the kinetic energy lost will equal the sum of the initial kinetic energy minus the sum of the final kinetic energy. Now we remember that kinetic energy is 1/2 mv squared. Now we know the masses of all of our objects. We know the velocity initially for both of the objects. After the collision, we only know the velocity of the first mass. We haven't been told the velocity of the second mass. So what we have to do in order to solve this problem is use conservation of momentum in order to find the velocity of my second mass, and then I can use that in order to find the kinetic energies of the initial and final system and subtract the two to get the energy that I lose. All right, so this is where we're trying to get to. We've got to find the velocity here of my second mass in order to get there after the collision. So V2 final equals question mark. All right, so to find that velocity of my second mass after the collision, we have to use conservation of momentum. And conservation of momentum says that the sum of all the momentum in my system before the collision equals the sum of all of the momentum after the collision. Now, momentum was mass times velocity. So the sum of the initial momentums of my system is going to be M1 V1 initial plus M2 V2 initial. That's the momentum of mass 1 plus the momentum of mass 2 before the collision. And that has to equal M1 V1 final plus M2 V2 final. So that's the sum of the momentums for both of my object after the collision. Okay, now we can go ahead and make this a little bit easier for ourselves. Let's see, our initial velocity for the second ball was 0. It was at rest. So this term will be, that velocity is 0. So then this entire term is 0. And remember, we're trying to solve it for the velocity of my, my second mass after the collision, V sub 2 final. So I can subtract M1 V1 final from both sides. And so then I have that M1 V1 initial minus M1 V1 final equals M2 V2 final. Now I can divide both sides by M2. Divide both sides by M2. So V2 final equals M1 V1 initial minus M1 V1 final all over M2. Now, I know that sometimes, when I'm solving these problems, I will flip my quantities around the equal sign. Okay, I have all stuff over here equals to all stuff over there. And it's okay if I flip stuff around the equal sign. In math, we call that the symmetric property. So if I say, here I could call this whole side A. If A is equal to B, I can flip it and say that B is equal to A. And that's perfectly okay. It's called the symmetric property. So oftentimes in class, I will flip things around the minus sign or equal sign. I like to put the thing that I'm solving for out in front of the equal sign when I can. And so I do that a lot of times in class, and I don't necessarily mention that, but that's what's happening. You can totally do it. It's perfectly okay, and it's called the symmetric property if I do that. Now, if I look back here, we said that the masses of both of my balls were the same. And since M1 is equal to M2, I'm dividing both of these terms by M2. So actually, I can cancel out all of those masses here. So actually, V2 final is just going to be V1 initial minus V1 final. Okay? And so V2 final will equal the initial velocity of ball 1, 3.98 meters per second, minus the final velocity of ball 2, which is 0.3 meters per second. So V2 final equals 3.98 minus 0.3, which is 3.68 meters per second. So we found V2 final equals 3.68 meters per second. All right, now I can use that in order to find the difference between the total initial kinetic energy and the total final kinetic energy. Now I've run out of room here, so I'm going to erase this side, and we're going to start a new side over here by solving for these initial and final kinetic energies, so we can get that energy lost. We just found the velocity of ball 2 after the collision, 3.68 meters per second. Now we can go ahead and get the sum of the initial and final kinetic energy. So let's look first at the sum of our initial kinetic energies. Sum of our initial kinetic energy is going to equal 1/2 M1 V1 initial squared plus 1/2 M2 V2 initial squared. All right, so that will equal 1/2. The masses are both 0.37 kilograms times the initial velocity of ball 1 was 3.98 meters per second, and we square that, plus 1/2. The mass of my second ball was also 0.37 kilograms times its velocity initially. Oh, well, its initial velocity was 0 for the second ball, so I actually didn't need to write that, but this term is actually 0. So the initial kinetic energy is 1/2 times 0.37 times 3.98 squared, and that will be 2.930 joules. That's the sum of my initial kinetic energy. Now let's do the sum of my final kinetic energy. So that will equal 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared. Right. So we'll do equals 1/2 M1, which is 0.37 kilograms, times V1 final, the final velocity of ball 1 after the collision, 0.3 meters per second squared, plus 1/2 times m2, 0.37 kilograms, times the final velocity of ball 2, which we just found, 3.68 meters per second squared. All right, and then that will equal altogether 2.522 joules is the sum of the final kinetic energy after the collision. So to get the energy that we lose, we're just going to subtract these two quantities. We're going to subtract the sum of my initial kinetic energy, 2.930 joules, minus the sum of my final kinetic energy, 2.522 joules, and then that will give us the kinetic energy that we've lost in the collision, which is going to be 0.408 joules. Okay, so where did this energy go? This energy can get transformed to another type of energy instead of kinetic energy. So often during a collision, the kinetic energies can get transformed into thermal energy. You can lose energy through heat. You can also lose energy through sound, through vibration, through kind of deforming the objects as these objects slam into each other. Those are a couple of ways that you can lose energy. The majority of collisions that are going to occur in your everyday life are going to be inelastic collisions. We're going to lose some energy during that collision to other forms of energy. Away from kinetic energy, you'll take some of that kinetic energy and transform it into sound, heat, changing of the shape of objects. The energy does not disappear into the universe. It just changes from one form to another form of energy.